Good morning, good evening, and good afternoon, everyone. Welcome to the 11th episode of the second season of the Young Researchers Forum on Detonation. Today is our honor to have Professor Huangwei Zhang to share us about his work on detonation propagation in dilute n-heptane sprays with and without pre-vaporization. Dr. Huangwei Zhang is an assistant professor from Department of Mechanical Engineering, National University of Singapore. He received his bachelor's degree in engineering mechanics and a master's degree in fluid mechanics in 2007 and 2009, respectively, from the School of Aeronautics Science and Engineering, Beihang University. He worked as a research associate in the State Key Laboratory of Turbulence and Complex Systems, Peking University from 2009 to 2011. He obtained his PhD degree in energy and combustion from the Department of Engineering, the University of Cambridge in 2015. He then stayed from 2015 to 2017 in University of Cambridge to take up a postdoctoral research associate position on pulverized coal combustion. Dr. Zhang's research fields are detonation, combustion theory and modeling, multi-phase combustion, multi-phase thermal fluids, and sprays in manufacturing and materials science. And now I will give the podium to Dr. Zhang. Please go ahead. Thank you.
Hello everyone in the meeting room. So I'm Huangwei Zhang from Singapore. So may I take this opportunity to thank Xiaocheng and his colleagues to organize this forum, this platform for us to exchange the research experience with each other. So today I want to share our very recent results about detonation propagation in dilute n-heptane sprays with and without pre-vaporization. So this work was mainly performed by the research fellow in Singapore, Zhang. Actually, he has already moved to Beijing Institute of Technology. I think he will start just this month. So since actually, these results are very new, so any suggestion, comments, and criticisms are welcome. Okay. So in this talk, I will introduce firstly the background and the previous studies about spray detonation. Okay. And then I will introduce the governing equation. We mainly use the Eulerian-Lagrangian method and also a numerical solver. So in the third part, we will talk about the detonation propagation in dilute fuel sprays. Okay, so finalized with some observations about from a numerical simulation. So for detonation wave in liquid sprays, we can very easily have two practical applications. The first one is about the safety engineering, like the explosion of the vapor clouder, okay, or explosion of the flammable gas, okay. So for the vapor clouder, sometimes probably, we will have the condensed fuels. So it is very likely for that case that detonation will not propagate in a fully homogeneous mixture. So we will have the liquid, okay. And another one, actually, nowadays in order to reduce the greenhouse gas emission, we are always talking about the decarbonization. We are always talking about hydrogen or ammonia. So in order to utilize these views, okay, so a very important aspect is the safety, okay, safety issue. So as you may know, actually, the water spring system is a very important way to inhibit like hydrogen fires, hydrogen explosion, okay. So for that case, actually, the detonation, the hydrogen detonation will propagate also in the mixture with water droplets. Okay, so this is the first case. Then the second one is for the propagation. Nowadays, and more actually, people are interested in the detonation-based propagation system. Okay, like detonation, rotating detonation. Sorry, I used like. Okay, so can you see the red dot, right? Like the rotating detonation and the passive detonation, they are actually well known for their high combustion efficiency, okay? So nowadays, actually, lots of work lots of the detonation experiments are performed based on hydrogen or other, simple hydrocarbon fuels like methane or ethylene and so on. Okay, so actually to commercialize these novel technologies, use of the liquid fuels is almost a must. Okay, like diesel or like kerosene or something like that. Okay, so actually we have already some studies about the liquid fuel RDE, liquid fuel also RDE here based on the experiments done by the Russian colleagues and this work, and also the liquid fuel PD. Okay, so in detonation in spray fuels. Okay, so in this system we have the lead shock wave, we have the follow the reaction wave, and we also have the word droplet. Okay, so there will be complicated interaction between the detonation wave and the word droplet. Okay, so it is much more complicated than the gaseous detonation. Okay, so for this phenomenon, actually, what are our existing knowledges? Okay, so it is very interesting for us to look back about the research history. Okay, about the research history on spray detonation. Okay, so here I summarize the previous work after World War II till now. Okay, about the detonation in heterogeneous mixtures. Okay, so this is the time axis. Okay, from around 1960 and till now. Okay, so there are many samples here with different colors. Okay, so the green color means review. Okay, review paper, and the yellow means simulation. The red one means experiments. Okay, and the white one means theory. Okay, so this actually here it is before this point last century. Okay, last century. And after this point, this century, okay, this century. So we can see here, in last century, there are many theoretical work and focused on the structure of detonation, in dilute sprays, and also reaction zone structure. Okay, and there are also some theoretical work about the cylindrical detonation wave and also the reaction zone in the cylindrical detonation wave. Okay, so most of this work were done by two institutes. Okay, so the first one is University of Michigan. Okay, and the second one is University of Connecticut. Okay, Connecticut. So then we moved to 1980s. So from 1980s to from 1980 to 1982, researchers from Israel, okay, Edelman and Burkett, did some simulation work about the blast-initiated normal heptane detonation. Okay, so they have several papers published in AIAA, and at that time, I think their work are quite impressive. Okay, with relative detailed model and show good agreement with experiment data. Okay, then in this century, actually, in 2002, there is a review paper. Okay, but mainly focused on the PD. Okay, in that paper, there are quite a lot of discussion about the liquid fuel utilization in PD. Okay, in PD. And then we have we further have some numerical simulations about the liquid fuel detonation in tubes. Okay, fundamental study performed by the colleagues from, I think, naval research. Okay, and then we have a review paper here. Okay, after this we have more and more simulation work. Okay, more and more simulation work. So like the CESC modeling work. Okay, and in recent years, we also have some spray detonation in with liquid fuels, like for the ODW, the oblique detonation wave, okay, performed by the colleagues in China, and also for in US, okay. And the latest work, actually, it's hydrogen detonation in water sprays, okay, performed by the Japanese colleagues Watanabe, okay, Watanabe. So if you look at this time here, time history, okay, if you look at the timeline, you would see actually, we need to think about what is actually, the underlying driving factor, okay. You may want to look at the milestone, for the first successful PDE or RD experiment with liquid fuels, okay. So yes, so okay, I added it here. So I added 3 square symbols here. The first one is a liquid PDE. PD experiment, okay, reported, okay, and so it is here around in 2003, okay, and the next one for the liquid RD from the Russian colleagues, okay, it is in 2006, okay, 2006. We also have a report actually from the colleagues in University of Michigan, okay. So it is in 1973, okay, performed by Zhang and Adelson, okay. I think it is funded by NASA, okay, it is funded by NASA. So you see here, once the liquid fuel RDE TD was successful, and more what comes out, okay. So there are several key words for the past work, like some of them focus on the detonation reaction zone structure based on theoretical work, and also detonation initiation, like this work, and also the detonation cell size, okay, in the aerosol detonation tube, okay, and also the spray droplet properties, like the very early one and the very latest one, okay. So now, okay, at the beginning of the second decade of the 21st century, we need to think about okay, what we can do, okay, for the spray detonation, okay. So now, as I mentioned in the last slide, so more and more actually, attention to the detonation-based propulsion system, and the hydrogen as a fuel becomes more and more important. So our knowledge for spray detonation actually is it's in high demand. Okay, so in spite of lots of work listed here, there are still lots of unknowns. For example, like the detailed detonation structure. Okay, so how the detonation and the spray droplet interact with each other. Okay, so we can still do. There are still lots of work can be done. Okay, so for this talk, okay, so I will try to study the following aspects. Okay, the first one is the effects of the liquid fuel spray property on the detonation propagation. And the second one is detonation extinction and reinitiation in fuel sprays. So they are the unsteady detonation dynamics in a heterogeneous mixture. The last one is the two-phase coupling between the fuel droplets and the detonation wave. Okay, so here we will use the hybrid Eulerian and Lagrangian method with two-way coupling. Okay, and we will also use a two-dimensional configuration. Okay, so this is about the objective and the method. So for the Gamma equations, we use for the gas phase here. I think here I don't need to repeat and then one by one. So the only thing I want to highlight is the reluctance here. So since we consider the two-way coupling, so we have the interface terms like as mass, as momentum, as energy, and as species. Okay, so these terms represent the interface coupling between the fuel, between the gas phase and the droplet phase in terms of the mass, momentum, energy, and the species. Okay, so this for the gas phase. And for the liquid phase here, we use the Lagrangian method. Some of you may be familiar with this method. So it is standard. Actually, the Lagrangian method is used to check the dispersed liquid phase. So the liquid phase is composed of a large number of the spherical droplets. Okay, so here the droplets can be physical or modeled ones, as I will introduce later. Moreover, we use the point force approximation. So when I say point force approximation, it means actually, the droplets are not resolved by our grid, by our safety mesh. Okay, they are so-called subgrid droplets, and the droplet volume fraction on the gas phase are not considered in this case. So if you look at this this equation here, we don't have the the volume fraction in the governing equation. Okay, so this is okay for the dilute regime, dilute droplet regime. Okay, here we use the partial concept, or you may want to say that it's a partial method. So the partial here is a group of the liquid droplets with identical properties. It is actually, it's a model. Okay, it is a model. So for one partial, look at the figure here. Okay, so the blue dots are the droplets. Okay, they are the physical droplets. Okay, so the red dashed lines are partials. Okay, so this partial includes many droplets. Okay, many droplets, and these droplets, okay, they behave identically. Okay, I will introduce this method later in a separate slides. Okay, so for each partial, we will solve the governing equations. Okay, so like the mass, momentum, and energy. Okay, so since with this method, we don't need to solve the governing equations, the ordinary differential governing equations for each droplet. We only need to solve the governing equations for the partials. Okay, so the computational cost and also the data storage space will be reduced considerably. Okay, so you may want to ask, so how about the accuracy? Okay, so we will compare later. Okay, so here the mass and the MD is the mass droplet, and this is the UD for the droplet velocity and also for the droplet temperature. Okay, for this term, for the momentum, we only consider Jack. Okay, Stokes Jack force. Okay, and for the droplet temperature, we only consider the convective heat transfer and the latent heat. Okay, latent heat. So here, because now we have two phases. Okay, so two different sets of equations, partial differential equation for the gas phase and ordinary differential equation for the droplets. Okay, so here we solve them in solver with coupling. Okay, with coupling. So here we develop a so-called the central form based on open form here. And for this form, we aim to solve the multi-phase, multi-species compressible reacting flow. Okay, so for this solver, we have two parts with some coupling here. So the first one is a Eulerian solver for gas phase. Okay, solve the gas phase equation, solve the Navier-Stokes equation. And for the Lagrangian solver for the liquid phase, it is used to check the parcels in the flow field. Okay, so they are coupled with mass, momentum, and energy. Okay, so these terms are reflected in this source term or sink terms here, the red guys here. Okay, so for each solver, we have different modules. I will not try to introduce one by one. Okay, so for chemistry here, we can use detailed chemistry or global chemistry. Okay, and shockwave is actually it is a Masco type scheme. Okay, and for drag force, it's for the Stokes model, and for heat transfer, it is a Rens-Michel. Okay, and for evaporation, actually we use the Sirignano model. So so for this solver, I think you want to know it is okay or not, it is accurate or not. So we did quite a lot, validation and verifications. I will not try to introduce in this talk. Okay, but if you are interested, you can scan this code to have more details there. We listed all the validations and verifications there. Okay, and this accuracy and for the efficiency, recently we tested in our Singapore supercomputer and also in the Japanese Fugaku supercomputer. Okay, so we can use about 8,000 processors, and with this we still have the linear speed up. Okay, for more processors we haven't do it. Okay, so basically this solver is developing and evolving. When I say developing and evolving, we always include new features for detonation modeling, and the new features we tested recently is the ASET and the DAT, the Institute Adaptive Tabulation, Dynamic Adaptive Chemistry. Okay, so we aim to increase the efficiency for detailed chemistry integration. Okay, but for these two features we will not use here. I just introduce here. Please keep tuned. Okay, so this is a physical problem. Okay, so this is a two-dimensional problem, and it's a rectangular domain. Okay, rectangular domain. It can be divided into two parts. The first one is the Java section. Okay, so this is a gas-only section. Okay, and the second one is gas-liquid two section. Okay, so the Java section, the first section is 0.8 meter. Okay, 0.8 meter long. Okay, and the two-phase section is 0.2 meter long. Okay, so for the gas phase in the Java section, in this section, it is gas is normal heptane and air mixture, and the equivalence ratio is 0.6. Okay, it's fixed in this work. Okay, in this work. And for the two-phase section, we will vary, some parameters. Okay, so here we have the few droplets and air and fuel vapor. Okay, so this fuel vapor are pre-vaporized. Okay, initialized. Okay, so here for the equivalence ratio for the gas phase in the two-phase section, we consider two values. The first one is 0.6. So that means actually we have some level of pre-vaporization. And the second case is 0. Okay, 0 means we don't have any pre-vaporization. We only have droplet, pure spray. Okay, pure spray. So in the whole domain, the initial temperature is 300 K. Okay, 300 Kelvin. And the initial pressure is 0.5 atmospheric. Okay. For the gas phase chemistry, we use two-step. Okay, two-step chemical mechanism, 5 species. Okay, so there are 2 reactions. The first one is normal heptane oxidized to CO. Okay, and the second one is CO further oxidized to CO2, and the second one is reversible. Okay, so the kinetic parameters are from Westbrook and Zhang. Okay, and also from the Ponson's paper. Okay, and we made some validations in our recent paper by Meng. Okay, so it is published in Physics of Fluids. Okay, so this for the gas phase, and for the detonation here, we use 3 points to initiate the detonation wave to achieve cellular structure within a relatively short distance. Okay, so since the gas phase equivalence ratio is always 0.6 for the Java section, that means the incident wave to the two-phase section is the same for our simulation. Okay, for our following discussion. Okay, for the liquid phase, mono-sized dilute fuel droplets. Okay, so uniform distribution in this area. Okay, so second, the droplet size we consider here is 2.5 to 20 micrometer. Okay, not very big. Okay, not very big. So liquid fuel equivalence ratio here, phi L is 0 to 4. Okay, so here we can say quite rich phi L. Okay, I think 5G, no need to introduce. Everybody knows from the combustion textbook. So phi L, I listed the definition here. When we estimate phi L using this equation, it is assumed that the volume of the droplet is neglected. Okay, so it is applicable for dilute sprays. Okay, dilute sprays, and we can further define the total equivalence ratio from phi total from phi L plus phi G. Okay, so the value here, because this is a fixed 0.6 and phi L is this range, so phi total is 0.6 to 4.6. Okay, so in this work, actually, we didn't consider the droplet breakup. Okay, so I understand actually, in the recent literature, we have some colleagues considering the droplet breakup, and this is interesting, and we will also consider in our future work. Okay, so you may want to ask, what does dilute mean? Dilute means actually the droplet in our simulation does not affect each other. Okay, they don't collide with each other. Okay, so this actually is a qualitative description. If you want to have a more quantitative description, you can look at this figure from closed book. Okay, so this is a particle volume fraction alpha. This is the particle diameter d. Okay, So they have different regimes. This is dilute, this is dense. Okay, so tau v, we can compare the relation between tau v and tau c. Okay, tau v is the momentum relaxation time scale. Okay, and tau c is the interdroplet collision time scale. Okay, so if the if the interdroplet collision time scale is much longer than the momentum relaxation time scale, then the droplet collision is not so important. Okay, not so important. So if we sketch the range of the particle volume fraction and the particle diameter in this diagram, it is almost here. So it is dilute. Okay, it is dilute. Okay. So this is a physical problem. Before I move to the simulation results, I want to discuss numerical implementations. The first one is the numerical puzzle and the physical droplet. Okay, and the second one is the mesh resolution. Okay, so as I introduced just now, we use the puzzle method. So we call it a numerical puzzle. In some literatures, they call it like a model model droplet or virtual droplet, but I think it's essentially the same. Okay, so here these are the droplets and these are the puzzles. So we group some of the droplets into one puzzle. Okay. Then we check the puzzle instead of the physical droplets. Okay, so then a problem comes out. Okay, a problem arises. So what is a good number for us to have the droplets in one puzzle? Okay, so there is NP here. Okay, NP actually it's a parameter need to be checked. So this is the number of the physical droplet for each puzzle. Okay. So we did some tests. Another 2 points I want to mention here is the first one is how to represent the spray droplets in CFD actually needs modeling. Okay, you can check the physical droplets in the CFD work, no problem. Okay, but actually this will be very expensive. Okay, even in the very simple spray system, the physical droplet can be millions, or you will have millions or billions of droplets. Okay, this one. So the second is the droplet effect. The droplet effect on the gas phase are statistical, and also the cell size level. So statistical means when we have many droplets, even for the dilute spray problem, we still have many droplets. So we need to consider the effects of the droplets on the gas phase in a statistical way instead of one droplet. Okay. The second one is the cell size level is the droplet only affects the cell, the flow field in the cell it belongs to. Okay, it belongs to. Okay, so it will not affect the property. It will not directly affect the property for the nearby cell. Okay, for the nearby cell. Okay, so here we did some tests here. We choose one case. So for the droplet diameter, initial droplet diameter 5 millimeter, and 5G is 0.6, 5L is 0.4. Okay, so this is the time series for the evaporation rate and for the heat transfer rate. Okay, so we can have two cases. The first one is NP equals 1. So NP is the number of the droplets for each parcel. Okay, and the second one is NP equals 8. Okay, so for the first one means one droplet parcel, one parcel, one droplet. Okay, so for this case actually it's 2 million parcel. Okay, 2 million droplet, not too many in this case. Okay. And the second one for the red line here is NP equals 8. So much reduced to 0.3 million parcels. Okay. So if you can, and these properties are volume integrated in the two-phase section. Okay. So we can see here for the two-phase interaction and also for the heat release rate from the combustion, they are quite close with each other. Although they have some, differences, okay, some small differences, okay. So this for the numerical particle and physical droplet. So in our following case, we use NP equals 8 here. Okay, NP equal. But for this number, actually, it depends. It depends. Okay, different cases. In different cases, different values of NP can be used. Okay, so based on our research experience, NP less than 30 is a good approximation. Okay, so but you can't use very large NP here. Once you use very large NP, that means actually you group many droplets in one parcel. Okay, so for many locations, actually it is gas only. Okay, it is gas only. So this probably there's a limit of the numerical parcel method. Okay, so this the first numerical implementation issue, and the second is the mesh resolution. Okay, so here I call it a mesh resolution dilemma. Okay, for spray detonation. So this actually, the schematic of the spray detonation, we also have some droplet here. So shock wave and the droplet evaporates and the diameter becomes smaller, and the reaction wave and the smaller droplets. Okay, so then this is the grid. Okay, so for the gas phase, I think everybody here have very hard resolution. Okay, maybe tens of micrometer or even smaller. Okay, once we have the very small resolution, we can resolve many details near the detonation front. Okay, and which is particularly important, if you want to capture the unsteady detonation dynamics. Okay, like extinction or reinitiation. Okay, so this for the gas phase. Okay, we hope many cells within the half reaction length. Okay, the induction length. Okay, for the droplet phase, the mesh cannot be too small. Okay, we hope actually the CFD cell is reasonably large. Okay, relative to the droplet size, droplet diameter. Okay, because if you look at it here, okay, this is a CFD grid. This is the droplet. We need to calculate the evaporation. For example, we need to calculate the evaporation. We need to simulate the evaporation and heat transfer. All these processes actually are surface process. Okay, surface phenomenon. However, in the CFD simulation, at least in the Eulerian-Lagrangian method, we need to interpret. We have to estimate the gas properties. Okay, from the gas phase at the droplet location. Okay. So if actually, the cell size is very small, the interpretation from the gas phase, okay, may be problematic. Okay, maybe problematic. So for this phase, we hope, larger cells, okay, compared to the droplet diameter. Okay. So in this sense, actually, you may want to ask, what kind of range, we can use? So we can look at this spray droplet diameter spectrum. Okay. So this actually they have two lines here. Okay, this is a millimeter and this is a micrometer. Okay, so this is a 1 micrometer. Okay, and this is the 100 micrometer. Okay, and sometimes we call it aerosols, very small droplets, and this from nozzle, and the larger one from sprinkler systems. Okay, so for the Lagrangian modeling, normally we consider like 1 micrometer to 100 micrometer. Okay, so for the larger ones, probably you need to consider the interface tracking. Okay, so for the smaller one, probably you need to consider the Nuisance number effect. Okay, so for this range, if you would like to make your cell size much larger, okay, or at least larger than this range, it's probably a tens of micrometer. Okay, tens of micrometer. And if we also consider the half reaction length, okay, so I sketched it here. So for hydrogen, it is quite small, maybe 1 micrometer. Of course, it depends on the operating conditions and the composition. Okay, and for heavy hydrocarbon like the normal heptane here, it can be 1 millimeter. Okay, or maybe higher than 1 millimeter. Okay, so if you would include many cells here, okay, if you include many cells here, then your grid should be less. If the half reaction length is 100 micrometer, then at least if 10 grids, then the cell size should be the mesh size. Okay, the mesh cell size, it should be like 10 micrometer. Okay, then for the droplet diameter, it's very close to the droplet diameter, like we consider in this work. Okay, so what I want to see here, it is a dilemma. Okay, I want to see here is the range of the reasonable mesh resolution is quite narrow. Okay, it's quite narrow. So it is very difficult for us to take care of two ends very well at the same time. So what we can do is to try our best. Okay, so in this work, actually, we use a 100 micrometer by 100 micrometer. Okay, it is a two-dimensional domain. Okay, so the half reaction length for the gases a normal heptane air mixture with equivalence ratio of 1, it is 0.3 millimeter. Okay, it is I think everybody knows that the dependence of the HRL on the equivalence ratio is U-shaped. Okay, it's U-shaped. So if you have because this 0.1 micrometer and this 0.3 millimeter, okay, so we have at least 3 or 4 points here. And for the field reach and field link conditions, okay, we will have more grids. Okay, so like for the half reaction length for 5 equals 0.6 it's over 10. Okay, it is over 10. And this grid actually is 5 times larger than the maximum droplet diameter we consider. It is which is 20 micrometer. Okay, so we tested this grid first for the gas phase. Okay, so 2 cases. The first one is 0.6 and 1.0. Okay, so we calculate the cell size and propagation speed using the above mentioned two-dimensional configuration, and we compare our results with the theoretical values from S2 box, and in general, it is quite close. Okay, so here the cell size estimated by Eddie's model. Okay, it is quite close, and we also tested the two droplet-Lagrangian case. Okay, so we half the mesh size. We use the 100 micrometer and 50 micrometer. Okay, and we checked that the numerical soot for. And at the same time, we check the distributions of the interface exchanger terms. Okay, so here is the evaporation rate, and this is the heat release rate from the combustion, and this is the heat transfer rate between the gas phase and also the droplet phase. So the black line here is the 100 micrometer, and the red line here is the 5 mesh. Okay, in general, actually they are quite close. Okay, they are quite close. So this for the to implement issues, two numerical configurations for the parcel and for the mesh resolution. Okay, so in the following, I will introduce our results. So this is the detonation propagation speed. So for the left figure, this is the total equivalence ratio, and this is the droplet diameter. Okay, calculate three groups. Okay, so group 1, 2, 3. Okay, so for this group, for each group, actually, they have the same diameter, same initial droplet diameter, but with increased liquid fuel equivalence ratio. Okay, so for the leftmost point, it is 5L equals 0, means no droplet. Okay, no droplet, but 5G equals 0.6. Okay, I want to remind you. So for the rightmost point, 5L equals 4. It is very rich. Okay, the reason why we use such a rich equivalence here is we initially, we run simulation from here and then we push it. We want to see the extinction. Okay, so here this dashed line actually it's the demarcating line between the detonation propagation cases and the extinction cases. Okay, extinction cases. For these cases, we also color them with the propagation speed. Okay, so the red dots is roughly, here. Okay, roughly here. So we further visualize the dependence of the propagation speed on the total equivalence ratio. Okay, so here is 5T. Okay, for these three groups. Okay, these three groups. So the red line here is 0.5 micrometer. The blue line here is 5 micrometer, and the last one is 10 micrometer. So actually, for reference, for your convenience, I also listed the liquid equilibrium ratio here. So this is 0.6, and the first point here is 0. Okay, phi L equals 0. So this one is a gas only case. Okay, and here is 2.6. Okay, so what we can see here is for fueling composition. Okay, I mean phi T. Okay, less than 1. When we add droplets, okay, the propagation speed increases. Okay, increases, and then beyond this, it decreases. Okay, it decreases. Okay, and the second feature here is for the fueling cases, the propagation speed increases. Increases with decreases with initial droplet diameter. So for the red line here, the finest droplet, okay, they have the highest propagation speed. Okay, so for the largest one, they have the lowest. Okay, actually, this is the opposite for the fuel-rich cases. Okay, so for the fuel-rich cases, when the total equivalence ratio beyond a critical value, I think here is around like 0.8 or 0.7. Okay, so here, okay, here, like this, if you look at these 3 points, the propagation speed increases. Okay, with the droplet diameter. Okay, with the droplet. This actually associated with the evaporation of the droplet. Normally, we can say we can expect for the small droplet. Okay, it can evaporate very quickly. Okay, then lots of the vapor can be added to the mixture. Okay, the mixture. So this is actually for the total equivalence ratio. Actually, an interesting quantity here is the effective equivalence ratio. Okay, effective equivalence ratio, particularly near the detonation front. Okay, for the large droplets, we will see later. Actually, there are some residual droplets behind the detonation wave. Okay, so here is the general feature of the gaseous detonation. Okay, so this is the pressure, this is the temperature, and then this is the gradients of the density and the pressure. So the case here, we consider one case. The initial droplet is 10 micrometer and phi G 0.6, phi L is 0.4. Okay, phi T is 1, but for the phi L actually is fueling. Okay, so here the detonation front structure generally are similar to those of the detonation wave in gas-only mixtures. Okay, I have no chart to expand. So for the for more results here, the same case, okay, but for other quantities. The first one is the volume fraction. Normally, it is very low, okay? So it is beyond 0.1%, okay? Belongs to the dilute region, okay? And the second one is the Pmax, the peak pressure trajectory, okay? We always use this to check the triple point, okay? And this is the heat release, and this is the normal heptane. This is the normal heptane mass fraction, okay? So if you look at this figure again, near the triple point trajectory, here the droplets are evaporated very quickly, okay? With some fuel vapor here, with some unburned fuel vapor here, okay? And this actually, here actually, okay, so the second line here, are some interface exchange terms, okay? So this actually EVI is evaporation rate, okay? So HTI is the heat exchange rate, and the last two is the momentum exchange rate in the X direction and in the Y direction, okay? So this X direction, this is the Y direction, okay? So look at here, behind detonation wave, particularly behind the mass stem, okay? So the evaporation is quite strong. It's red here, okay? It is red. And this is the incident wave, okay? Behind the incident wave, actually, the droplets evaporation is not very pronounced, okay? It is not very pronounced. Actually, it is associated with the strength of the shock wave. The higher, the stronger shock wave will heat up the droplet quickly, okay, more quickly, okay. And a similar situation for the heat exchange. Okay, heat exchange. Okay, so for the momentum, we can see here, this actually, because this it is from minus to it is from negative to positive. Okay, so in our equation, actually positive means the momentum is transferred from the gas phase to the droplet phase. Okay, so sorry, the opposite. Okay, so for the negative values, which means that the momentum transferred from the gas phase to the droplet phase. Okay, so you can see here there's actually, you know, somehow like a demarcating line. Okay, so near the detonation wave, actually it is negative. Okay, so here the droplets transfer the momentum to the gas phase. Okay, to the gas phase. So actually you can see here behind the detonation wave, okay, the kinematic equilibrium is not reached. Okay, the global kinematic equilibrium is not reached. Okay, it is not reached. So this for the gas phase detonation. And here I have a movie to show you the detonation propagation in fuel spray and fuel spray air vapor mixtures. Okay, so this is the condition. Okay, so I will plate, and this is the gas temperature. Okay, this is the peak pressure trajectory. Okay, the numerical full, and the last one is the droplet volume fraction. Okay, so this line here is the initial two-phase contact surface. So this is the incident wave. Okay. So actually, you know, from the Java section to the two-phase section, there is a transition area. Okay, so in this part, the cell size is greatly reduced. Okay, it is greatly reduced. Okay, so this for the detonation in the fuel spray vapor and air mixture. So sorry. Okay. So here, I would like to further show the fuel droplet distribution behind the detonation wave. Okay, so here we consider three cases with different initial droplet size. This one is a 10 micrometer, corresponding to the case we introduced in the last slide. Okay, and the other two are the 5 micrometer, and the last one is 2.5 micrometer. Okay, so for these controls, the background here are the gradient of pressure. Okay, show us, you know, the distribution of the shock wave. Okay, and these are the Lagrangian droplets. Okay, these are the Lagrangian droplets. So you can see here, this is because this actually is the D0 is 10 micrometers. So here it is 10 micrometer, and when they cross the detonation wave, the reduction of the droplet diameter is not very pronounced. Okay, then starting from here, the evaporation becomes important. Okay, so then the droplet size reduce very quickly. Okay, reduce very quickly. So this actually, you know, behind roughly, you know, this line, behind this line, there is no any droplet. Okay, so the two-phase contact surface is moving together with the leading shock wave. Okay, together with the leading shock wave. So the variation of the droplet temperature can be also seen from this figure. Okay, behind the mark stem, the increase of the droplet temperature is very quick. Okay, it is very quick. And for the incident wave here, there is a very long, you know, induction period. Okay. So there will be some difference. There will be some difference. Okay, so when we have the smaller droplets, like if you look at here, the droplets can be evaporated quickly. Okay, than this one. Okay, the interesting case is the last one here. Most of the droplets can be evaporated near the detonation wave. Okay, near the detonation wave. Okay, so so you can see from here, actually the droplets heating and the evaporating zone changes with the droplet diameter. Okay, droplet diameter. So later I will visualize the evolution of the length of the droplet heating and evaporation zone. Okay, for different droplet diameters. Okay, then you will see actually it is there are some interesting features. Okay. So these are the numerical soot faults for more cases. So these are recorded from the trajectory of the peak pressure. They can be used to stand for the triple point trajectory. Okay. So here we consider 7 cases. Okay, 7 cases. The first one is they are varied from here. They are different. They are differentiated with phi L, liquid fuel equivalence ratio. Okay, so the first one is 0.4. Okay, and the last one is the 0.8. Okay, I would remind you here that all the images, okay, are extracted from a same instance. Okay, the same instance. So the location of the leading detonation, okay, leading shock front, roughly, can reflect their propagation speed. Okay, the propagation speed. So if you look at here, actually, the 0.8 runs fastest. Okay, this is the champion. Okay, this is the champion. So when the phi L increases, the cell size also increases. Okay, although because the incident wave is from here. Okay, it will take some finitely long transition period. Okay, so starting from here, we can see the obvious difference between different cases. Okay, different cases. When phi L is beyond some critical value, then we can see some detonation extinction and also reignition. Okay, if you look at the numerical flow for phi L equals 2.4. Okay, so here the detonation quenched, and then near this boundary we have a local explosion spot. Sorry, local explosion spot. Okay, and then it generates a very strong transverse detonation. Okay, this transverse detonation consumes the fuel vapor behind the leading shock, because at these locations, the leading shock and the followed reaction zone are decoupled. Okay, are decoupled. And for the last figure here, the detonation wave extinction the detonation wave is quenched. Okay, without any reinitiation. Okay, without any reinitiation. So we can further visualize the time series of the heat release rate. Okay, for all the cases I introduced just now. Okay, Z corresponds to a constant initial droplet diameter, and also 5G same 0.6. Okay, so here from 0.4 to the last one is 4.0. Okay, 4.0. And this is the time series of the heat release rate. Okay, so this heat release is integrated over the gas liquid to phase section. Okay, from excuse me, from 0.8 to 1.0. Okay, so one thing I'd like to mention here is the time series. Actually, the time interval of this time series is 1 micrometer. Okay, so some high frequency oscillations actually they are filtered. Okay, particularly for these cases. Okay, for like for the stable propagation cases. Okay, so for phi L less than 1.6, the detonations are stable, and we can see some small fluctuations from the heat release rate. Okay, and then for phi L is for phi L greater than 2.8. Okay, detonation extinction occurs, and when we increase phi L, okay, the extinction occurs earlier. Okay, so we can clearly see, for example, like the yellow one is 0.8, and then for this 0.3, so the extinction occurs at early instant. Okay, early instant. So here I further visualize a detonation extinction case in fuel-rich spray and a vapor air mixture. Okay, just now I visualized a stable case. So here is the extinction case. So likewise, this is the gas temperature, peak pressure trajectory, and the droplet volume fraction. Okay, so this is the initial two-phase contact surface, and this is the incident wave. Okay. So here you can see actually, the decouple of the leading shock wave and the reaction zone can be seen, and then the droplets are pushed, okay, by detonation. Okay, so here the volume fraction is slightly high. Okay, so this is the extinction case, and for the two-phase coupling, in spray detonation we have the besides the shock wave, because the reaction wave, we also actually have the two-phase contact surface. Okay, as you can see from the two movies I played just now. Okay, so this two-phase contact surface moves together with the detonation. Okay, and between the leading shock wave and the contact surface, actually, we can see this is a droplet evaporation zone, droplet heating and evaporation zone. Okay, as seen just now, this zone decreases. Okay, the length of this zone decreases with reduced initial droplet size. Okay, initial droplet size. So we further visualize, we further quantify the two-phase coupling. Okay, across this zone. Okay, so here when I say two-phase coupling, I mean the mass exchange, the momentum exchange, and also the energy exchange. So if you still remember, when I introduced the gas phase equation, we have several sync term source terms. Okay, so there as I think Sm, S, NH, and S momentum. Okay, so here we visualize this term and we integrate these terms across the width of the domain. Okay, and weighted by the density. So it is a Favre average. Okay, it is Favre average. And three different cases corresponds to these three diameters. Okay, 25, 5, and 10. Okay. So what we can see here is this is the heat release rate. Okay, we use this actually, to denote the reaction zone. Okay, the reaction zone. So for each case, actually, roughly the leading shock wave is here. Okay, and the reaction zone corresponds to the peak of the heat release rate. Okay, so what we can see here is in any cases, actually, the kinematic and thermal equilibrium between the gas and droplet phase behind the detonation wave not reached. Okay, not reached because of the finitely long relaxation time for both process, and at the same time because of the highly evolving distribution of gas velocity and gas temperature behind the detonation wave. Okay. Another feature we can see from this figure is the evaporation. The evaporation rate and the heat transfer rate decreases with D0. Okay, so decreases from the increases with D0. Okay, increases with D0. And for the momentum exchange, it is interesting. So near the detonation wave, it is negative. Okay, so the momentum actually transferred from the gas phase. Okay, so droplets are accelerated. Okay, however, immediately behind this area, we will have a positive zone here. Okay, so that means actually these droplets can accelerate the gas there. Okay, accelerate the gas there. Okay, so for each droplet, actually we can also see this kind of phenomenon. However, when the droplet size is increased, the positive momentum exchange is reduced. Okay, it is reduced. So this for the two-phase coupling. Okay, so here I further visualize the this is actually, the evolutions of the droplet heating and evaporation zone. Okay, so this time and this distance, and this distance corresponds to the to that between the leading shock wave and the contact surface. Okay, so it's a roughly, it corresponds to the droplet heating, the length of droplet heating and evaporation zone. Okay, so there are two groups. The first one, the dashed line is the large droplet, 10 micrometer. Okay. The solid line, small droplet, 5 micrometer. So we consider 4 cases for each. Okay, for phi L from 0.4 to 1.6. Okay, so what we can see here is this section corresponds to the detonation is just still in the driver section. Okay, so at this location, at this instant, the detonation wave enters the two-phase section. Okay, so we can see actually a transit period exists for increases of the heating and evaporation zone length. Okay, however, the transit period is it's different. Okay, it is different. For example, for like this one, it's quite short than the large diameter. Okay, large diameter, and then the length of the droplet heating and evaporation zone keeps constant. Okay, keeps constant. Okay, so this actually also similar, although we can see some differences here. Okay, differences here. So this is the evolution of the droplet heating and evaporation. This is important because this is directly associated with the two-phase exchange. Okay, the moment, the mass moment, the evaporation and the momentum exchange and the energy exchange. Okay, energy exchange. So up to this point, we discussed the detonation propagation in pre-vaporized n-heptane air mixture. So here I will also introduce the propagation in pure sprays. So here, when I say pure sprays, I mean there is no any pre-vaporization. Okay, so only in droplets. Here we have 4 images here. They correspond to phi L equals 1. Okay, equals 1. So phi G is 0 because it means that actually we don't have any pre-vaporized gas. Okay, so similar to so here all the images are from the same instant. Okay, so this propagates fast. Okay, so when the actually sorry. So when the droplet diameter is small, actually the droplet the detonation wave detonation propagation speed is faster. Okay, it is faster. So when we increase the droplet diameter, we can see some unsteady phenomenon. For example, like this case here, D0 equals 10 micrometer. So because I would like to remind you here is that this actually in the two-phase section. Okay, so the detonation from here, it's propagating detonation. Okay, from normal heptane air mixture with equivalence ratio of 0.6. Okay, so for this case, actually, the detonation first quenched. Okay, and then reignition at some point. Okay, reignition some point, and then propagation. Okay, continuously. So basically, this is the same case for the 15 micrometer. Okay, 15 micrometer. Because here we only visualize until this instant. So we further run this case. Okay, the detonation wave will be initiated at a later instant. Okay, for these 4 cases, we also quantify the time history of the heat release rate. So here the heat release rate is also a volume integrated value. Okay, over the two-phase section. Okay, so from 2.5 to 15. Okay, so we can see here for the first 2 cases, it is generally it is a continuous propagation. Okay, but for the third one and for the first one, we have first extinction and then reinitiation. Okay, so with increased droplet diameter, okay, the reinitiation instant is delayed. Okay, it is delayed. So this results corresponds to the extent from 0.8 meter to 1 meter. Okay, so this is one question actually. If we propagation further, how it will evolve. Okay, this is one interesting question. And the second one is, if we further increase the droplet size, let's say like 20 micrometer. Okay, if we can we also see the extinction and the reinitiation? Okay, maybe the reinitiation, maybe it will not reinitiated, maybe it will reinitiated at a later instant, but beyond this computational domain. Okay, we haven't done this test. Okay, but we will do we will do later. Okay, so here this is a movie for the detonation and propagation in pure sprays. Okay, so the droplet diameter, initial droplet diameter is 10 micrometer. Okay, no any pre-vaporized gas, and the liquid equivalence ratio is 1. Okay, so here is the gas temperature, and the next one is the droplet volume fraction. Okay, so this is a propagating detonation wave. Okay, and this is the initial two-phase contact surface. So we will look at how it will evolve. So now actually, we can see the decoupling, okay, between the leading shock and the reaction zone is very obvious, okay. And then the detonation wave is initiated and successfully propagate. Okay. For the large droplet, we always see, the detonation extinction and the reinitiation. So next slide, and this is also the last slide. Okay. I understand I run out of time, so I will go through this very quickly. Okay. So we extract some instant here. Okay, for the last case. Okay, so this point A extinction case, and from A to F. So okay, don't also mark it here. Okay, so initially, it is decoupled very. We can see, we have a diffraction surface here, and we can also a diffraction surface here. Okay, and then at this instant, actually, we can observe local explosion. Okay, so this local explosion actually developed very quickly. Okay, and evolved into a transwave, a strong transwave detonation. Okay, so this transwave detonation actually consume the fuel vapor between the leading shock and the product gas. Okay, and then fully develop the detonation wave DT2. You can observe here, propagate further across, across this area, consume the droplet here. Okay, droplet here. Okay, so this is actually all what I want to share in this talk. Okay, we use the Eulerian-Lagrangian method to model the detonation propagation in dilute normal n-heptane sprays. Okay, we will discuss the dependence of the detonation propagation speed on the droplet properties, and we also observe the unsteady detonation dynamics like the extinction and reinitiation. Okay, we also discuss the evolution of the droplet heating and evaporation zone, and also the two-way coupling. Okay, so the last one actually, we also predicted the successful detonation in pure spray. Okay, so actually, the pure spray is more relevant for the practical scenarios. Okay, and when the fuel jets are large, detonation extinction and reinitiation are found. Okay, So these are actually our very recent work, and I think we have lots of future work. Okay, need to be done. So, for example, we will include we will use the detailed chemistry. Okay, with like RSET or DAC, dynamic adaptive chemistry for better capturing gas chemistry. Okay, and the second one is the droplet breakup and collision. I believe when we include the droplet breakup, the few droplets were broken into smaller or much smaller ones when they cross the leading shockwave, and it will burn more effectively. Okay, and then the next one is the pure spray. Okay, this is actually very important for practical scenarios. The last one is dense spray. Okay, this probably we will do in the long. This is actually a long-term plan. Okay, this is a long-term plan. Okay, so thank you very much, and sorry I keep you so long. Okay, thank you very much.
Yeah, thank you, Professor Zhang. It's very interesting and very informative talk, and we already have quite a few questions from chat. I believe there are a lot of very detailed questions from Sandeep Damati, and I see a relatively short question from Ahorn. I didn't see his last name. Maybe I will let he go with this shorter question about OpenFOAM first, and we'll let Sandeep to go through his detailed comments and questions.
Okay.
Yeah, Ahorn, would you like to ask it directly, or you prefer me to read the question? Okay, I guess I will just read. His question is, hello, Professor Zhang. Is RY row central foam two-phase solver available for low-speed cases? And have this solver test the case of Achenbaum in OpenFOAM tutorial? How about the results?
Actually, it is mainly developed for high-speed flows. Okay, we haven't, to be honest, we haven't used it for low-speed flows. Mm-hmm. Yeah, so the existing validation and verifications are mainly done for the compressible flows, like shock capturing schemes, also like the chemistry integration method, and also for the droplet, some models like evaporation and heat exchange. Okay.
Okay. Yeah. Thank you. Thank you. And Sandeep, would you want to ask your question directly?
Yeah. Thanks. Yeah. Hi. Very interesting work. So I have a couple of questions to begin with. So can you go to slide 13?
Okay. Slides 13. This one, right?
Yes. Yeah. So you show that for large droplet sizes, the speed actually decreases, right? So is this because the droplets cross the so-called sonic plane? I mean, my question is basically how far downstream does the droplets propagate in each case? If the droplets cross the sonic plane, whatever the fuel is behind the sonic plane doesn't get coupled, doesn't get burned, or doesn't get coupled to the shock wave. So that's why do we see the reduction speed because of that?
You mean here? You mean the 10 micrometer, right? The black line, right?
For all the cases like 2.5 to 10 micrometer, how far downstream does the droplets propagate before they get completely evaporated?
Actually, when the droplet increases, when the field reach conditions, right? So because here actually 5G is fixed. So when we increase the 5G, that means we increase the phi L. Okay?
Yes.
So yeah. So when we increase phi L, that means actually more droplets are added in the system. Okay.
Yes.
So if we so for the case of D0 equals 2.5 micrometer, then more fuels can be when the fuel vapor is added in the system, then the total equivalence ratio actually is getting richer and richer. Okay, qualitatively. Okay, yeah. near the detonation wave. Okay, I think this is true for the 2.5 case, but for the larger droplet, like for 10 micrometer, it will take finitely long distance for the droplet to be heated. Okay, and then started to evaporate. Okay, Okay, so I think this is actually caused by the filtration effect. Okay.
Yeah. So did you try to quantify like how far downstream does the droplets propagate before they get completely evaporated? Like, do we have any length scale measurement?
We haven't discussed this, but if you look at you can see my slide, right?
Yes. Yes.
Yeah. So if you look at this size and this droplet size, this actually, most of the droplet can be vaporized near the detonation wave. Okay. However, for this one, you can see the evaporation zone, the droplet evaporation roughly start from here. Okay.
Yes.
And the evaporation, the length of the evaporation zone is about 2 millimeter. Okay. Yeah, roughly from here to here. Okay.
Yeah.
But this actually, yeah, go ahead. Sorry.
So do you have an estimate of how far is the sonic plane, at least in the 1D ZND calculation? Because my wondering is if, yeah, go ahead. So my question is basically if the droplets are, if they cross the sonic plane before they get evaporated and convert into gaseous fuel, I mean, we are losing all the heat that is present inside those fuel droplets. Like those droplets are good for nothing. So my question is, do we see that here? Is that why we see the reduction in the propagation speed?
Okay, so for this, actually, the length scale estimation, we haven't do this. Okay, but we can do it later. Okay.
Okay. Yeah, that would be interesting. So my next question is, if you go to like slide 14, or even this, any slide is present. Yeah, the one with droplets. Yeah, we see like significant particle clustering here. So did you try to quantify what is the particle clustering here? And does this particle clustering break the model locally? Like, do you see like the droplet volume fraction increasing significantly in a computational cell beyond the permissible values?
I think we have a distribution of the volume fraction. This one.
Yeah. So
yeah. So this is instantaneous distribution of the volume fraction. Okay.
Okay.
Right. Yeah. So we can see some regions with high volume fraction, red color here. Okay.
Yes.
Yeah. But even for this locations, actually, it is still much lower, than the volume fraction limit suggested by Crow. Okay. So for Crow, actually, as suggested by Crow, we normally, we hope the volume fraction should be less than like 0.1%. Okay.
Yes.
Yeah. Because for our modeling method, actually, it is for dilute spray. Okay.
Yes.
So this is still okay for that.
Okay. So my other question is, so if you go to your problem setup, I see that, so I see that the droplets, the two-phase section is only like 20 centimeters in your problem. Is that distance sufficient enough for the detonation to reach like a steady state? Or to put it differently, if I increase this two-phase section from 20 centimeters to let's say 40 or 60 centimeters, do you see any change in your results? Can we claim that this 20 centimeters is sufficient enough for all the cases for the detonation to reach a steady state?
Okay, so for most of the cases, we have tested that it is okay. Actually, it is sufficient around for us to discuss the phenomenon. Like for this one, okay, for this one, okay. And actually, I also mentioned this for this case. So for this case, because this is a pure spray, so we for the larger droplets, right? We observe the extinction and reinitiation, and for larger droplets, we observe extinction and delayed reinitiation. Okay. So if we consider larger droplets, probably it is we need to use a longer computational domain. Okay, computational domain.
Okay.
We will test it. It is actually it is in question. Okay.
Okay. Yeah.
Yeah. To capture the unsteady process.
Yeah. So my next three questions are based on just numerical convergence. So you hear the grid size is like 100 micron, if I'm not mistaken, right?
Yeah.
And that gives I don't know, 5 cells per induction length.
At least.
Yeah. I mean, so in your calculation, so my first question is, how does the induction length change between, so when you did, you must have done like 1D ZND calculation, right? You got, let's say, a induction length, initial induction length, but when you run the 2D simulation, I imagine the induction length gets longer as the droplet size increases. So computationally, it's beneficial. Like in reality, you have more cells per induction length. To put it differently, did you do any kind of resolution study? Like, did you go from 100 micron to, let's say, 50 and even below? I know it's constraining. You need to have a balance between what's your cell size and the droplet size. But did you try any kind of resolution study to show numerical convergence?
Yes, actually, I mentioned this in one slide. I think here we tested for the droplet Laden case and also compare, the numerical soot flow and also the two-phase exchange terms. So here is the 100, which is used in our simulations, and another one is half the cell size, so it's a 50 micrometer. So in general, actually, the numerical flow and also the results are presented here are, agree with each other quite good, quite well. Okay.
So did you try to compare like spatial scales, like cell sizes, and did the cell size change or does it remain the same? Because it's been established at least in gas phase detonations, that as you increase resolution, at least for unstable mixtures, you see that you get smaller and smaller cells. So there is no numerical convergence, at least in case of gaseous gaseous single phase detonations. So I was wondering if in terms of spatial scales, do you see any convergence here?
The distribution of the numerical soot flows, actually, of course, they are not identical, but actually they are quite close to each other. Okay. Yeah, because we refine the mesh, actually the distribution of the cell size will change. Okay.
Okay.
Yeah.
Yeah.
Okay.
The another question is, you didn't consider droplet breakup model, but I think it's a very significant phenomenon to consider in the future, because one droplet breakup can take significant from the detonation, so it can change the propagation speed significantly. So do you have any comments as to if you were to consider a droplet breakup model for this problem, what kind of droplet model would you think would be the best suited for these high Weber number cases?
Okay, so there are quite, there are some breakup models, but most of them are based on some like the empirical constants for different regimes. Okay.
Yeah.
So in this modeling strategy, we can include them. Okay, and mainly based on the Weber number. Okay, different Weber numbers. Yeah. Okay. Yeah. So I believe when I include the droplet breakup, the droplets cross the detonation wave will be broken into smaller ones, okay, behind the leading shock wave, and then I guess the evaporation will be facilitated. Okay. Yeah. Probably the reaction zone, the length of the reaction zone will be shortened.
Yeah.
Yeah, particularly for the large droplets. For the smaller one, I'm not. I guess there is no big difference. But for the larger droplets, okay. Yeah. Probably we will see some difference. Okay. We will see some difference. Yeah.
Yeah.
We will test it in the future. Okay.
Yeah. Probably the last question is, so the droplet drag law. so you said it's just Stokes drag law, right? So it just depends on the particle Reynolds number. There is no Mach number dependency.
Yeah.
Don't you think the Mach number of the particle will play a leading role here in these high-speed flows in terms of drag?
For this one, actually, I think there is a paper from researchers in Office of Naval Research. So they tested actually a different drag model with some Mach number correction. So from their results, the difference is only limited to the shock wave.
Mm-hmm.
Yeah. Okay. Yeah.
Okay. Mm-hmm.
So, but in general, you know, the current model based on the Reynolds number, based on the Joubert Reynolds number, can capture quantitatively, can capture, you know, the Joubert velocity and also the in-phase coupling terms quite reasonable. Okay, quite accurate.
Okay. Mm-hmm. Yeah. Okay. Yeah. Thank you.
Okay. Thank you.
Yeah, thank you, Sandeep, for your question, and Professor Zhang for his answers. Are there any other questions from the audience?
I see we have one new question from Wenqin Wang.
Oh, yeah. Okay. Yeah. Wenjian, you can ask directly. Yeah.
Sure. I can ask this question myself. So my only question is from a very fundamental numerical learning position. That you show some governing equations from your Euler equations with some source terms in the beginning, and you also introduce some governing equations in the Lagrangian layer, which computes your droplet size, the temperature, and the momentum, or the velocity of each parcels. And but I would also like to know how did you quantify this source term in terms of the solutions in your Lagrangian layers, and how did you update your Lagrangian layers in terms of your gas dynamic solutions? That's it.
Okay. So here you mean source term, these terms, right?
Yes.
Okay. So these terms, for example, I just give you an example here. So this SMS, right? So SMS actually is the evaporation rate, okay? Because this is the this is the gas phase equation, okay? So finally, you know, we will discretize this equation for each CFD grid, right? For each CFD grid. And then if we look at this one, so this is a CFD grid, okay?
Yes.
Then SM is a sum of all the droplet evaporation, all the evaporation rate of all the droplets belonging to this CFD cell, and that's it. And same for other terms.
Got it. But how did you compute this evaporation rate in terms of the temperature side?
Okay, for the evaporation rate, actually we need a model. We need a model. We can go back to this slide. So it is from m dot. So m dot actually is estimated based on the. Here we use the Sirignano model. So it depends on different properties, different like gas and properties. Okay, like for the Sheldon number and for the diameter. Okay, and also for the droplet Reynolds number and something like that.
Okay, thank you so much.
Professor Zhang,
thank you.
Sorry, I also have a few questions.
Okay.
The first one is just based on this slide. You show that in this Lagrangian model, basically there is a mass change due to evaporation, but in your momentum and energy equation, the mass are treated as a constant when you compute this this velocity and temperature change.
Yes.
But in fact, there's also a part of momentum and energy change due to the mass change of the droplet. So actually the MD term should go into the derivative. But I think this might be an okay approximation for energy, but for momentum, because like particle or the droplet is getting lighter and lighter. So there is a momentum exchange due to the reduction of the droplet mass, right? So I think a more accurate model would be like actually tracking the momentum and the internal energy of the particle instead of only the velocity and the temperature, right? Like
you mean
actually,
so you mean put MD
right.
inside the derivative here, right?
Yeah.
Yes.
Because like if you write the energy balance equation, then there are actually two derivatives. One is the derivative of U, the other is the derivative of MD. So
okay.
yeah, it's kind of like a chain, a product rule of the derivative. Yeah, I don't know how much that would affect on the result, but just in terms of the formulation, I think that's physically more accurate.
If we put the MD inside the derivatives, and then it's dMdt UD over dt. Okay, so if we use chain rule, then we will have two terms. One is dut dt. Another one actually is ud dmdt, right?
Yeah.
Yes.
But in fact, like in the simulation itself is only tracking the time rate of change of momentum, and that equals to the force. So you don't really need to separate those into two terms. But eventually it will be just one term, but instead of tracking U as the variable in your model, you track momentum UD, right?
From my understanding, you are correct. So if you put the MD inside the derivative, so you will have two terms. The first one is a D, so M dot D UD over dt, and then the second one is UD dmdt. So UD dmdt actually is a UD M dot. So basically, actually, we neglect this terms in this in the existing formula here in equation 7, right?
Right.
Yeah, this might be, it's compared to this one, it's not so important. Yeah, this is my understanding.
Right.
Okay.
And my other question is about this dilemma you talk about this resolution. I think it's very good, like you put in this explicit way, and I saw there are a lot of literature or people doing simulation. They try to hide this problem from the readers, but I think there's another important length scale between your reaction zone length and the particle diameter, which is particle spacing, right? Because
particle spacing, okay.
Yeah, like the average spacing among one particle to its neighbors, right? So so I think like if the grid size is much smaller than the average particle spacing that you can calculate based on the equivalence ratio and the particle size, that means this parcel approximation or parcel methodology is invalid, because if you consider this parcel, you are kind of like enforcing that this 8 or how many number of particles are within a close neighborhood, but this might be much smaller than the physical particle spacing associated with the equivalence ratio and the particle size you assigned to the problem. So I think
there are some this is actually one of the methods, to let's say it is model the effect of the droplet on gas phase, right? Yeah, I think the reason why they developed this is to ensure the numerical stability for the gas phase equation, right? Yeah, but for my understanding, actually, for example, like this one, in one grid, we have one droplet, so if actually the effect of the droplet on the gas phase is local, it only affects this directly, affect this area, right? However, if the CFD grid is quite big, or if you have some modeling, let's say have some model to average this effect in a large area, Yeah, from numerical point of view, the solution procedure will be more stable. However, this actually we lose the localness from the geopolitical effect. Actually, yeah. So these actually, I also mentioned in this slide. Actually, there are different methods here. Like one of them is PSR, particle source in cell method.
Right.
Yeah. This. Okay.
Okay. Thank you. Thank you for your answer. I may have one very quick comment again. Actually, it's also a question that I'm not very sure about. If evaporation is the only physics that make this droplet go into gas phase, I think I heard about this oxidative pyrolysis. That is, I think that's somehow considered in some liquid jet fuels reduced kinetics, right? I don't know, that kind of like a chemical process also governs this gasification of the droplets.
Yeah, this I think this is another way, I guess. But here, an effect should be included probably in your mechanism, right? Yeah. So here, evaporation is the only way to have the fuel vapor, okay, from the liquid phase to the gas phase. Yeah.
Okay.
Yeah.
Fine. Okay, thank you for your answers.
Okay.
I have another comment from Professor Chinaya. Ashman, would you want to ask it directly, or do you want me to read? Maybe I just read his comment. He said a very simple for breakup can be found in Vanatabi et al.'s paper based on experimental timescale for breakup downstream of shocks.
I think it's a comment to Wenjin Wang's question earlier on.
Right. And he also posted the a link or the title of the article.
Thank you.
Okay, yeah. Yeah, thank you very much, Prof. Chinaya, and also Dr. Watanabe. Okay, you saw the paper from Shockwave, right?
Yeah.
Yeah, we will read it.
Yeah.
Okay.
Yeah.
Okay.
Yeah, thank you. And are there any other comments and questions? If not, then I guess I'd like to thank Professor Zhang again for his time preparing this talk and giving us this very informative webinar on his research work. And I would also like to thank everyone for attending today's webinar. And our next episode will be on next Friday by Professor Miles Bohom from Berlin, talk about his work on RDE. Yeah, I will call it the end of this webinar. Thank you all again. Have a good day.
Okay, thank you. Bye-bye.
Yeah, bye-bye. See you. Bye. Bye.